In this video, I want to talk about Dalton's Law. I know I said we were only covering those 4 laws, right, or 3 individual laws, and the ideal gas law, but I actually lied to you, sorry. We're going to talk about Dalton's Law also. And Dalton's Law applies to a mixture of gases, so instead of just oxygen or just hydrogen, a mixture of those. So we're essentially taking the gas laws that we already have learned and we're extending them to a mixture. So Dalton's Law of Partial Pressures is our full title. And what this law tells us is that if we have a mixture of gases and we know the individual pressures of each individual gas, so if I had a mixture of oxygen and hydrogen and I knew the pressure of oxygen and then I knew the pressure of hydrogen, that if I was to add those pressures together, I get the total. So essentially, P total is equal to the pressure of my first gas. Let's actually just put a 1 there. So the pressure of my first gas plus the pressure of my second gas. If I had 3 gases, we just continue to add them together. So my total pressure, right? The total pressure of a mixture of gases is equal to the sum of the individual gases' pressures. Those individual pressures are called partial pressures. So the individual pressures. So in my little formula up above, right, this one, these ones here, I'll try to fit it in somewhere. These are my partial pressures. So essentially, if you add up all the partial pressures, you get your total pressure. Pretty straightforward law. So an example for us. If we have a mixture of 3 gases and the pressure of the first gas is 0.764 atmospheres, the pressure of the second is 708 millimeters of mercury. We'll do some unit conversions here. And the third gas has a pressure of 0.62 atmospheres. And then our question, of course, what is the total pressure of this gas? So it's literally just adding them together. The only problem is they all have to have the same units, right? If we're going to add something, our units have to be the same. So I do need to do a couple conversions, right? I have 0.764 atmospheres. I have 708 millimeters of mercury and 0.62 atmospheres. So before I add those together, right, they need to be the same units. We can't add or subtract numbers if their units aren't the same. We can multiply them, our units that are just the 2 different units multiplied by each other then, but to add them we actually have to have them the same. So I do need to do a conversion. I didn't specify in the problem what I wanted our answer to be in. I could have said have it, in millimeters of mercury or kilopascals even, but I didn't. Because I didn't, we can do whatever we want. So since I have 2 of them in atmospheres and 1 in millimeters of mercury, I'm going to convert the 1 to atmospheres instead of doing 2 conversions. So I do know that there's 760 millimeters of mercury for every 1 atmosphere. And that would be provided. You don't need to memorize that number. So it's just a real quick dimensional analysis step, right? Just one step. I take my given 708 millimeters of mercury. Since millimeters of mercury are on the top, we have to divide by it, right? So 760 goes on the bottom, and 1 atmosphere goes on the top. So 708 plus 760. Oh, not plus, divided. Wow. Divided by 760. And I get 0.932 atmospheres. So now that I have that, we can just add them together. So 0.764 plus 0.932 plus 0.62. And then those are all going to be in atmospheres. Do be careful when we're adding them together. Our significant digit rule for this is the number of digits after the decimal point. So because 0.62 is only 2 digits after my decimal point, I do only want 2 digits after the decimal point in my answer. So 2.32 atmospheres is my answer. So the other way I could ask a question involving Dalton's law of partial pressures is I could give you the total, and then I could give you the partial pressures of all the gases except for one. You would then subtract to figure out the missing partial pressure. I'm not going to do an example like that because it's pretty straightforward, just kind of the opposite of the addition one, right? If we know the total but we don't know one of the partial pressures, you would subtract instead of adding them together. I do want to talk a little bit about mole fractions, and then we're going to actually relate that to Dalton's law. So mole fraction is actually another unit of concentration. We talked about molarity as a unit of concentration in chapter 7, right? The number of moles of solute I have per liter of solution. Mole fraction is another way we can express concentration. Our symbol for mole fraction is an X, and X is equal to the moles of the component gas divided by the total number of moles. And by the component gas, it just depends what gas I'm trying to determine the mole fraction of. So I had a mixture of helium and nitrogen, and I wanted the mole fraction of nitrogen. The moles of nitrogen would go on top, and then the total number of moles would go on the bottom. If I wanted the mole fraction of helium, then the moles of helium would go on top, total would go on the bottom. So moles of the component gas, whatever gas it is that I'm trying to determine the moles of. We could write it X1, saying we're talking about gas number 1, and then N is what we're using to represent moles in this chapter, right? 1, so the number of moles of that gas divided by N total. So mole fraction, what part is literally that, right? It's the mole fraction. It doesn't have units because it's moles over moles. It's literally just a number less than 1. So moles of our component gas on top, total moles on the bottom. All of the mole fractions, right, if we were to figure out if I had a mixture of 2 gases and I had the mole fraction of both of those gases, they're going to add up to 1 when we write it. So we're going to relate this to Dalton's law here in a minute. I do want to add just one more thing. If I was to take my ideal gas law, PV equals nRT, I am going to rearrange it to solve for P. So I'm going to divide both sides by V. And then I'm going to rewrite this a couple different ways. It turns out that if you were to plug in the moles of one of your gases in the mixture and then solve for pressure, you get the pressure of that individual gas, so the partial pressure. If you were to plug in your total number of moles, then you actually get your total pressure. So we could say that P total, right, if we have a mixture of gases, what is my total pressure, is equal to N total. So I would have my total number of moles multiplied by RT divided by V. If I wanted the partial pressure of one of my gases, I would plug in the number of moles of that particular gas times RT divided by V. So I'm going to do another rearrangement. I'm actually going to solve for N, and it might be easier if we actually just take our, if we take our original equation, solve that one for N. So I want N by itself. So I'm going to take PV and divide it by RT, right, if I want to solve for N. And then I'm going to write this the two different ways, where if I plug in the partial pressure of one gas, I get the moles of that gas. If I plug in the total pressure, then I get the total number of my moles. So it's really just this part rewritten solving for N. So we're just doing a little bit of algebra. So if I put a 1 here, I get a 1 here. If I do N total, I get P total, and then V over RT. If we go back up to my mole fraction equation, right, my mole fraction, X, is equal to N1 over N total. So if I was to take these two, divide them by each other, I made that line a little bit too long for me to write, I actually get my mole fraction. So we can do some reducing. It's the same volume, right? I haven't changed containers. I've only talked about, is it the moles of one gas or is it the total moles, right? They're still in the same container. So those V's are the same. They can go away. Same temperature, those can go away. And my constant is, of course, the same. So that can go away. Rewriting that, what I have is that P1 over P total is equal to my mole fraction, which is kind of a cool equation. We can actually determine the fraction of the moles by dividing the total pressure into the partial pressure. This equation is on the back of your periodic table, but it does solve it for P1. So it's written as your partial pressure is equal to your mole fraction multiplied by P total. And it honestly might be in the opposite direction. It could say P total times X, but it's the same thing. So kind of new equations that we've had. I feel like I need to make a little summary for you because they've been all over the place. So I have that P total, we'll just do Dalton's Law, is equal to P1 plus P2 plus P3 plus however many gases you have. If you have 10 gases and you knew the partial pressure of all 10 gases, add them together, you get the total. We have that we can get our mole fraction for our gas by taking the moles of that gas and dividing it by our total number of moles. We also have that we can get the mole fraction by taking the pressure of a gas and dividing by our total pressure. And then I just rewrote that second equation, the last one there, a couple different ways. So these are our new equations from this section. So an example, a particular gas, particular is a mixture of gases, has a total pressure of 5.83 atmospheres. Oxygen is one of the gases in the mixture, and its pressure is 0.21 atmospheres. So we're just going to use this equation here. We're solving for mole fraction. We have the total pressure and we have the pressure of oxygen. So my mole fraction of oxygen is going to be equal to the pressure of oxygen, so 0.21 atmospheres, divided by my total pressure, 5.83 atmospheres. And again, my units cancel, so I'm just going to have a decimal less than 1, right? Just a fraction. So when I divide this out, 0.036 is my answer. So that's the fraction of oxygen in that gas sample. So a more involved example for us. So we have a mixture of gases that contains 12.45 grams of hydrogen. And I'm actually going to just write these out because we are going to convert them to moles, so I'm going to leave myself some work here, or room for work. 60.67 grams of nitrogen and 2.38 grams of ammonia. And we want to know what is the total pressure and the partial pressure of each gas if they are in a 10.00 liter container at 90.0 degrees Celsius. So there's a couple different ways that we can solve this problem, right? We're looking for total pressure, and then we're also looking for partial pressure. I am going to have to convert these to moles either way, but what we can do is we can use the ideal gas law, PV equals nRT. And again, if we were to plug in the moles of each gas separately, so we would do this 3 times because we have 3 different gases, we would get each partial pressure. To get the total pressure, then we would just add those 3 numbers together. Our other option is we can do this once, putting in the total number of moles to get my total pressure. We can then figure out the mole fraction of each individual gas. And then remember, if we were to take P total and multiply by my mole fraction, I get the individual partial pressures. So a couple different ways to do it. Some semesters I do it one way, another semester I do it the other way. Normally I let the class decide how you guys want to do it. Since you're not here with me as I'm making this, I'm going to pick. And I'm going to choose to do the ideal gas law 3 times and then add them together. It would be really good practice for you though, because you never know if I'm going to ask something using this, to then try it the other way and see that you get my same answers. So I really would highly recommend that you do that. It is very possible like something like that might show up on a future assignment. So the first thing I'm going to do is just convert these to moles by dividing through by the molar mass of each gas. It is H2, so don't forget there's 2 hydrogen. N2, so 2 nitrogen. And then ammonia. So dividing those out. I get 6.16 moles of hydrogen. 2.165 moles of nitrogen, and 0.140 moles of ammonia. So these would be my individual number of moles. So the reason I'm going to do this the way that I want it, that I had said I was going to do it, is I can kind of take a shortcut. So what I'm going to do is I am going to solve for P, so I'm going to actually rearrange it. So P is going to be equal to nRT divided by V, but I'm going to factor this out it's going to be the same thing. I know that R, T, and V are not changing, so what I'm going to do is actually get a number for that. Instead of having to type in R, N, T, and V into my calculator for all three calculations, I'm going to like pre-solve for that, and then I just have to do it once. I'm essentially taking a shortcut. You don't have to do it this way. If it's confusing, then just, do it the longer way. But I like to do it this way better. Do note my volume is already in liters. My temperature, however, is in Celsius, so I do need to add 273 to that to convert it to Kelvin. Remember, our temperature always needs to be in Kelvin, so 363 Kelvin. So if I was to take R and then multiply it by my temperature, and then divide it by my volume. And I probably should have left units in here. Let me rewrite it with the units. I can only take so many shortcuts on you. 0.08206 liters atmospheres. I think I wrote that incorrectly the first time also. Moles K. And then my temperature, 363 Kelvin. And then my volume, liters. That's liters. So we're gonna get a number for that. Remember that's this RT over V part. And again, you don't have to do it in the way I'm doing it. You can type that in every single time. So you could plug in your moles for hydrogen, R, T, and V, do all the math, and that's gonna be equal to your pressure of hydrogen. You could plug in your moles for nitrogen, plug in R again, plug in T again, divide by V again. That's going to be equal to your pressure for nitrogen. I'm just choosing to not plug that in 3 times, but to just get a number and then plug that one number in 3 times. It's just, for me, it's just less work and it makes sense. If it doesn't make sense to you, then don't do it that way. You have to be able to reproduce these on your own on an exam, so you need to do what makes sense for you. So I'm getting 2.9798, I guess, when I round for sig figs. And then the units, these liters are canceling, and these kelvins are canceling. So my units on this are actually atmospheres per mole, which will make sense when we do the rest of the problem. I do want to double check my math on that, though. Yep, 2.98. So to get my pressure of hydrogen, I'm going to take my N, right, my number of moles for hydrogen, which I have up here somewhere, 6.16. And then when I multiply it by the 2.98, which is RT divided by V, atmospheres per mole, then my moles cancel. So my pressure for hydrogen, 6.16 times 2.98. I get 18.4 atmospheres. I'm going to do the same thing with the other ones then. My pressure for nitrogen, right, is going to be my number of moles for nitrogen. So if I go back up here, 2.165. And then multiply that by 2.98 atmospheres per mole. And again, that's just saving me from having to type in R, T, and V every single time. And when I do that, I get that my pressure for nitrogen is 6.45 atmospheres. And then we're going to do it one more time for ammonia. So I'm going back up. I'm finding my moles for ammonia, so 0.140. And then I'm multiplying that again by my RT divided by V, which we pre-worked out. And my moles will cancel. And I get 0.417 atmospheres. So these would be the partial pressures of each gas. The problem also wanted the total. So Dalton's Law, we just add them together. And I get that the total is 25.3 atmospheres. Again, remember when we're adding for number of significant digits, it's the number of digits after the decimal point. So here I have 1, here I have 2, here I have 3. So I want 1 after the decimal point. So this would be my answer. So again, this is one way to solve it. I really would like you to try it the other way also. So what you're doing the other way is you're going to use this equation, right? My ideal gas law, so PV equals nRT. You're actually going to plug in the total number of moles. And when you do that, you're going to get out, you're solving for P, you're reading out the total pressure. So I got the total pressure last, right? I solved for the individual pressures and then added them together. The other way, you're actually going to get the total pressure first. Once you get the total pressure, you're then going to go over and use this equation. You're going to multiply the total pressure by the mole fraction for each gas to get the partial pressure. We haven't actually calculated mole fractions that way yet, but remember, and I'll go up here to do it, wherever I can find room, my mole fraction is going to be the moles of whatever gas I'm talking about over my total number of moles. Right, that's going to be equal to X. So you would add all three of those together, the 6.16, the 2.165, and 0.140 to get the total, right? Total is literally the total. And then to get the mole fraction of hydrogen, you would take 6.16 and divide it by that total. Once you got that number, you would come down here, multiply that number by the total pressure that you got over here to get the partial pressure of hydrogen. You would then do that again. You would put the moles of nitrogen on top, total number of moles at the bottom, to get the mole fraction of nitrogen. Then back down here, multiply that number by your pressure, your total pressure, to get the partial pressure of nitrogen, and then repeat for ammonia. So please give that a try.